Hello, today I'm going to talk about the first experiment of Alain Aspect. Before we talk about Alain Aspect's first experiment, I'd like to briefly talk about the history before his experiment was published. The first thing we need to know is the concept of quantum entanglement. Quantum entanglement is a phenomenon in which when one particle is split in two and placed at a very long distance, if the spin direction on one side is decided, then the spin direction on the other side is fixed to have reverse direction immediately. For example, if you put one quantum on Earth and the other quantum entangled with it in a distant universe a million light years away, when the quantum in the Earth is observed to be spin up, then the quantum in the distant universe becomes spin down simultaneously. That is because according to quantum mechanics, each of these photons is governed by a same wave function. In response, in 1935, Einstein, Podolsky, and Rosen published the EPR paradox, arguing that quantum mechanics was not a complete theory. According to the theory of quantum entanglement, information transfer regardless of the distance and time of entangled particles is a phenomenon that violates Einstein's claim of spatial relativity and the principle of locality. At this point, the principle of locality is the principle of physics that objects that are spatially distant can never directly affect each other. In order for one object to affect another, the space between the two must be mediated. In other words, for interaction between objects, you have to give and receive something like light. This also violates Heisenberg's uncertainty principle. Quantum entanglement suggests that if you measure the momentum of A of the two particles, A and B, you can see the momentum of B without affecting the position of B. Therefore, you are fully aware of nature of B in reality. So you come to the paradox that principle of uncertainty is also incomplete. They saw that when the first entangled particles were formed, the information that the particles had already existed in the particles. So they are arguing that because of our lack of technology, we couldn't measure the hidden variables, but that information was already stored in each particle. In response, physicist John Bell suggested that the interaction between entangled particles can be demonstrated in the laboratory by measuring the spin axis. He showed that if hidden variable exists, as argued by the EPR paradox, the following inequality must be satisfied. Here, the term PAB is the average of the product of the measured value in the direction and the measured value in the B direction. Afterwards, four scientists, including John F. Clauser, further developed Bell's inequality and organized it into the following form. In more details, after particles have separated, one performs correlate measurements of their spin components along arbitrary direction vector A and vector B. Each measurement can yield two results denoted plus and minus. For photons, a measurement along vector A yields the result plus 1 if the polarization is found parallel to vector A, and minus 1 if the polarization is found perpendicular. For a singlet state, quantum mechanics predicts some correlation between such measurement on two particles. Let's denote P plus minus AB, this term, as the probabilities of obtaining the result plus minus 1 along direction A, and for particle 1 and plus minus 1 along direction B for particle 2. Then this quantity is the correlation coefficient of measurements on the two particles. In any case, it is important to note that if the value of S does not satisfy the following inequality, the realistic local theory claimed in the EPR paradox will be found to be false. Since then, many scientists have tried to recreate Bell's inequality in laboratories. Even before Alain Aspect's experiment, 8 experiments were conducted in the 1970s to reproduce Bell's inequality. The most famous of them is the Crowder experiment that you've seen earlier. Crowder's experiment also showed that quantum mechanics was correct, but it did not give a perfect answer. I'll talk about this in more detail later. Anyway, Alain Aspect was one of the scientists who wanted to experiment with Bell's inequality, and in recognition of that, he won the Nobel Prize in Physics in 2022. His experiments are as follows. First, he got two entangled photons from excited calcium atom. When the calcium atom is in the ground state, two electrons are spin paired in the outermost orbit. When one of these electrons observes light of suitable wavelength, it leaps into a high-energy orbit, in which the observed photons transmit information about the angular momentum quantum to the electrons that belongs to the atom, which appears as the angular momentum of the electrons in the excited state. Now suppose that the second electron, which remained in the ground state, leaps along its mate electron into excited orbit, while maintaining the direction of spin. In this case, the two electrons lie in the double excited state with a spin pair relationship. However, the electron pair does not stay in this state for long and immediately drops into its original ground state orbit, emitting two photons. In order for angular momentum to be preserved in this process, the two photons must be emitted in opposite states in the circular polarizing plate. Therefore, these two photons are entangled. Alain Aspect used two high-power lasers to produce excited calcium atoms. When a small box containing calcium gas was placed in a high-temperature environment and a laser is fired through a small hole, excited calcium atoms are produced in the forms of beams. When two beams intersect each other, atoms at the intersection observe and emit photons before colliding with each other. Then Aspect separated the light emitted in the opposite direction from the atomic beam into green and blue photons by passing through the filter. The photon then passes through two polarimeters and four photomultipliers, amplifying the signal, which is recorded in counting monitors. Let's find out more about his experimental device. First of all, this is Einstein-Podolsky-Rosenbaum experiment, which Alain Aspect used as the basis for his experiment. In his paper, he criticized previous experiments for not following this figure, or some experiments were performed with pairs of photons, but no efficient analyzers are available at such energies, and the results that would have been obtained with either polarizers or deduced indirectly from Compton scattering experiments. The validity of such procedure in the context of Bell's theorem has been criticized before Aspect's experiment. Other experiments before them were with pairs of low-energy photons emitted in atomic radiative cascades. True polarizations are available in the visible range, but this experiment also involves single-channel analyzer transmitting one polarization, vector A or B, and blocking the orthogonal one. Actually, that is the case for Crowder's experiment. The measured quantities were thus only the coincidence rates in +1 channels. Several difficulties then arise as a result of very low efficiency of detection system. The measurement of polarizations are inherently incomplete. When a pair has been emitted, if no count is obtained at one of the photomultipliers, there is no way to know whether it has been missed by the low efficiency detector or whether it has been blocked by the polarizer. Thus, coincidence counting rates such as this one and this one cannot be measured directly, so these kind of experiments need auxiliary experiments. So he proposed the experiment that followed this figure again, more ideally. Instead of using single-channel polarizers, he used two-channel polarizers, separating two orthogonal linear polarizations followed by two multipliers. In the following figure, you can see that the left has a single channel, while the right has two channels. So this is a four-fold coincidence technique. He could measure in a single run the four coincidence rate, yielding directly the correlation coefficient for the measurements along vector A and B, like this. Then, by changing the angle between two polarizers, it is able to repeat the same measurements for three other choices of orientation to test the CH-SH inequality. These procedures, he was able to not only to suppress possible systematic errors such as changes occurring when removing the polarizers. This is for the auxiliary experiments that is needed to previous single-channel polarizer experiment. Also, he could control more experimental parameters. For instance, he had checked that the sum of the coincidence rates of one photomultiplier with both photomultipliers on the other side is constant. He has also observed that the sum of the four coincidence rate, or plus minus AB, is constant when changing the orientations. Thus, the size of the selected sample is found to be constant. After building this theoretical foundation, it took as many as 5 years for the experiment to be realized. Afterwards, they conducted an experiment and published it in physical review letters, and the results are as follows. This schematic shows the correlation of polarizations as a function of the relative angle of polarimeters. The dotted curve is the quantum mechanical predictions for the actual experiment, and the big dots are real experimental result. We can see that the experiment is inconsistent with quantum mechanics. The more important thing to think is Bell's inequality. They conducted an experiment to verify the Bell's inequality, CHSH inequality, by changing the angle between the two analyzers into four angles. It has been seen earlier that the generalized inequality must be less than or equal to 2. However, their value was 2.697 and plus minus 0.015. Which resulted in a violation of Bell's inequality. The difference between the maximum allowed in Bell's inequality and the predicted value in quantum theory is 0.828. The value obtained by Aspect deviates from Bell's inequality by 83% of this difference. In quantum mechanics, 2.828 or 2 root 2 is value calculated under the assumption that the experimental equipment is fully functional. However, since there is no realistically perfect equipment, it is impossible to detect 100% without missing a single photon. The analyzer may also cause malfunctions, such as reflecting vertically polarized photons or passing through horizontally polarized photons, unlike the original intention. All of these errors are factors that make the finally obtained value less than the predicted value in quantum mechanics. Aspect described this as the visibility of quantum entanglement decreases. Aspect modified the predicted values by quantum mechanics, taking into account the limitations of experimental equipment, and the results were about 2.7, which was very accurate to the values obtained in the experiment. Eventually, Aspect, who obtained a value greater than the allowable limit in Bell's inequality, concluded the following. The results we obtained were almost consistent with theoretically predicted values in quantum mechanics, which is strong evidence to disprove all theories based on locality. In addition, it was found that the distance between experimental equipment had no effect on the entangled relationship for the particles. According to these results, photons are bound to each other in a mysterious way, and are described as a wave function until observations are made. When the observational behavior is involved and the wave function collapses, the photon is placed in a localized polarization state, which cannot be explained by the local hidden variable theory. The act of observing the polarization of photon affects the results obtained when the polarization of photon B is observed. No matter how far the distance between two photons is, this fact does not change. Therefore, this effect must be transmitted faster than light. After all, nature was originally non-local and called spooky. Alain Aspect experiment sparked another debate. Scientists supporting the local hidden variable theory argued that the polarimeter moved before photons were released from the calcium atom. As they claim, there is a possibility that photons will be affected by experiment equipment. This is called locality loophole. To solve this problem, Aspect conducted a second experiment. Thank you for watching my video.